Hi there. Once again, thanks for checking in. I hope you're doing well today. And this video here is going to be the second one in a short series of videos about special right triangles. This one, all I'm going to do really is show you some of the trickier examples. All right. And just a little bit of warning to get through some of these examples. We will be using some of the number tricks that we've been talking about concerning radicals, such as just simplifying a radical or writing it in a simpler way, or when you have a number divided by a square root. There's a thing that we've learned called rationalizing the denominator, which is just rewriting that fraction in a different way so that there's a whole number on the bottom of the fraction. So hopefully you're somewhat familiar with both of those little number tricks, and we're going to use them in some of these examples. All right, so the first set of examples is going to be about the 30, 60, 90 right triangles. So hopefully you recall that in this situation, the short leg we have been calling x. Whatever that length is, you double it to get the hypotenuse. And whatever that length was for the short leg, you just multiply it by the square root of 3 to get the longer leg. All right, so that's our pattern. We'll be using that in these examples. First one is where the hypotenuse is given to you as a number like 5, an odd number maybe. Well, all right, dividing an odd number by 2 means that you're going to have a fraction, but so what? 2.5. That's how long the short leg is. It's half as long as the hypotenuse, and the long leg is just that 2.5 times the square root of 3. You're done, pretty much. The only thing else I wanted to say about this is that you will see that number 2.5 times the square root of 3 written in a slightly different way as a fraction like that, 5 root 3 over 2. So just confirm for yourself that those two numbers are the same. Hopefully that doesn't trouble you too much. But you will see fractions like that in these examples that we're going to do here and in other material that you are likely to run into. All right? So just be aware of that. Next example is where the long leg is given to you as an integer like 12. All right, this might actually cause you a little bit of alarm because we are used to seeing that long leg have a square root of 3 tacked onto it, right? The short leg is x, the hypotenuse is 2x, and the long leg is x times the square root of 3. Well, what are we going to do with this? How are we going to find x? How am I going to figure out what that short leg is when my long leg is an integer? Well, if you think about this, what we're saying is that x root 3 equals 12, all right? Right there, just kind of put those two numbers in an equation, and what you've got is an equation just to solve for x. I need to know what x is. All right, well, that's not too big of an ask. We can solve that equation for x. First thing I guess we would do would be divide both sides by the square root of 3. Well, that isolates x right away on the left side and gives you a number like 12 over the square root of 3 for x. Well, so now what we're going to do is rationalize that denominator by multiplying the top and the bottom by the same number, the square root of 3. And so we get 12 root 3 over 3. Well, 12 over 3 cancels out or simplifies down to 4. So our actual final answer there is 4 root 3 for the short leg. And when you take that 4 root 3 and double it, you get 8 root 3. No big deal. All right, so let's do another one similar to that, just so you can see this routine that we just did. All right, let's say we've got the long leg now as a number like 27. All right, well, when you consider the pattern for that 30, 60, 90 right triangle, that means that x root 3 is going to equal 27. And we're basically going to repeat that same set of algebraic steps that we just did. Instead of having a 12, though, we'll have the number 27. So this is an algebraic routine, and when these algebraic routines become familiar enough, what you're doing is you're developing your own little shortcut. So I'm hoping that without me saying it explicitly right away, you'll recognize what this other shortcut is in these 30, 60, 90 right triangles. All right? So go through this routine here one more time. Divide both sides by the square root of 3. 27 over the square root of 3 can be rewritten as 27 root 3 over 3 by rationalizing the denominator. And 27 over 3 simplifies down to 9. So our final answer there for the short leg of this triangle is 9 root 3. And doubling it, you get 18 root 3 for the hypotenuse. Okay, so notice that pattern there. In the first one, we had a long leg of 12, and the short leg was 4 root 3. In the second one, we had a long leg of 27, and the short leg was 9 root 3. All right, so hopefully you're seeing a pattern right there. Let's try another set of examples. So maybe you can try this pattern out. All right, you may have noticed a pattern between the long legs value and the value of the short leg. All right, so I'm going to give you a moment to just kind of pause the video for a second to come up with the remaining side lengths on these triangles here. Okay, so maybe you've tried that, and hopefully, and I'm just going to jump to the answers here without a lot of explanation here. You may have noticed in that first one there that hopefully you got 6 root 3 for the short leg. 6 is 1/3 of 18, all right? And that is the pattern. That short leg is 1/3 of the long leg times root 3. I'm not sure if I said that exactly the best way. Let's look at another example. 60 is the long leg, so what's 1/3 of 60? Yeah, 20. So 20 root 3 is the short leg, and doubling that to get 40 root 3 is the hypotenuse, and you're done. Now, in the third example, 10 is not a number that is evenly divisible by 3. So what? It doesn't matter. You're still going to take 1/3 of 10, which is 10/3. Sorry, but it is 10/3. 10/3 times the square root of 3. And here's another example where most people would prefer to write that 10/3 times root 3 as 10 root 3 over 3 for the short leg. That's the preferred way. I don't really know why, but that is just the preferred way of writing that number. And so doubling that to get the hypotenuse is 20 root 3 over 3, and voila, you're done. All right? So let's take a look now at the 45-45 right triangle pattern. And you hopefully recall there that the two legs are the same. It's an isosceles right triangle, so those two legs are the same length. And the hypotenuse is the side length times square root of 2, x root 2. All right, so let's do an example here. And this time I'm giving you an example where the hypotenuse is 16. All right, so recalling our little number pattern there, that means that our x, which is the length of the legs, our x root 2 is equal to 16. And in the same way, we're going to solve that equation for x. All right, same kind of routine here. We end up with 16 root 2 over 2, which is 8 root 2. That's how long the two side lengths are, the two legs, excuse me. All right, so that's this same kind of pattern holds for 45-45 right triangles. And I'm going to leave it to you to try and observe this pattern as we go through some more examples. One of the problems, however, with square roots is that they don't always simplify in the same way. Some radicals do simplify, some don't. Some have factors of 4, some have factors of 9, or some other perfect squares, so they simplify in different ways. However, square roots are a fairly practical way to write the side length of a square. If, for example, you know the area of the square, you would take the square root of that number to figure out how long the side is. So since isosceles right triangles are half of a square, it is not unheard of or not uncommon to see square roots being involved with the side lengths, that is the legs of the isosceles right triangle. So we should get used to that. We should practice that a little bit. Okay, so we have one side there as 5 root 6. Well, obviously the other leg is also 5 root 6. And to get the hypotenuse, we're going to take that 5 root 6 and multiply it by the square root of 2. It doesn't matter. We still do the same thing to that number. That side length, that leg length of 5 root 6 multiplied by root 2, that gives you 5 root 12 for the hypotenuse. That's how long the hypotenuse is 5 times the square root of 12. However, the square root of 12 can be simplified down to 2 times the square root of 3. So instead of 5 root 12, we may have 5 times 2 root 3. Well, 5 times 2 is 10, so that means that our final result there is 10 root 3. Now, 5 times the square root of 12 is the same as 10 times the square root of 3. But, you know, this is just kind of a fact of life as a mathematician. Most mathematicians are going to prefer to write that number as 10 root 3. So you should just be aware so you're not confused, all right? That little simplifying a radical thing happens a bunch in this type of maths. Let's do a couple more. All right, there's 3 45-45 right triangles, 3 isosceles right triangles, and each one of them is going to be a little bit different. All right, here I'm giving you the hypotenuse is 5 root 6 for one of them, or on the next one there, a leg of 7 times square root 7, and then the third one there at the bottom, 3 root 2 over 4 is the length of one of the legs, all right? And I'll ask you to pause the video here for a moment and figure out the remaining sides of each of those triangles, all right? Give it a try. Alrighty, so hopefully you've tried that, and what you will see is that they all kind of work out in different ways. And that first one there, you end up with 5 times the square root of 3 for the 2 legs, all right? On the second one, the other leg is the same, 7 root 7, and the hypotenuse is 7 root 14, all right? So you may see some patterns in those two. However, those patterns don't always hold true for everyone. If you look at the third one, 3 root 2 over 4 as one leg means the other leg is also 3 root 2 over 4. And even though that's a weird fraction with a square root in it, I'm still going to do the same doggone thing. That is, multiply it by the square root of 2. 3 root 2 times root 2 is 6. And so when I carry that work out there, I get 6 over 4. I hope you can take a moment to confirm for yourself why that fractions, when you multiply all that together, you get 6 over 4, which I'm going to write as 3 over 2. All right, so if you look at these examples, there are some patterns, but they're not super consistent every time. It's hard maybe to see the patterns, for example, and so you just kind of have to take each one of these on its own. And hopefully that's enough. That was kind of a longish video there, so hopefully you hung in there with that and learned a few things, and I hope you're doing well. Stay positive and do some good math, folks. Bye-bye.